Okay, we're going to look at a few other things to consider. So the first thing is invariant points. So an invariant point is a point which does not move after it has been transformed. So an example of this would be if you're reflecting in the x-axis, any point on the x-axis would be an invariant point. It will stay fixed. So in this example it says find any invariant points on the transformation given by x dash equals 2y minus 3 and y dash is equal to x plus 1. Okay, so to do this, for the first one, we're just going to say let x equal 2y minus 3 and y equal x plus 1. So all I've done here is instead of saying it said x dash, I've just left that be equal to x, because if it's an invariant point, x will go to x, so x will not go to x dash, it'll stay put. So we've got two simultaneous equations. Call that dot 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 equation 1 dot 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 equation 2, and all we're going to do is rearrange and make these look a wee bit prettier. So my equation 1 is going to be x minus 2y is equal to minus 3. That's my equation 1, and then that's going to be x minus y is equal to minus 1, and that's going to be my equation 2. So all we're going to do now is add these two things. We're going to subtract them to get rid of them. So we'll just do equation 1 minus equation 2 and get rid of the x's. And you're going to have minus 2y minus y. So that's minus 2y plus y, which is minus y, is equal to minus 3 minus 1, which is minus 2. Therefore, y is equal to 2. Substitute back into equation 1. And the equation 1 then says x minus, it's going to be minus 4 this time, is equal to minus 3. So x is equal to minus 3 plus 4. So x is equal to 1. Okay, so in this one, my answer is 1, 2. And that's it. Okay, for the next one, for part B, exactly the same idea. Instead of calling the thing x dash, y dash, we're just going to say let xy equal 2 minus 1, 3, 4 times the xy times the xy plus 3 minus 3, and then all we're going to do is multiply that thing out. So we'll take a couple steps to do that. This is just a longer way to get to the simultaneous equations. So first thing is a 2 by 2 times a 2 by 1. It's going to be a column vector, 2x minus y, and then bottom line is going to be 3x plus 4y, and then plus 3 minus 3. So therefore that implies that x is equal to 2x minus y plus 3, and y is equal to 3x plus 4y minus 3. Again, we'll call that equation 1 and equation 2, and they need a lot of tidying up here. So we're going to say x minus y is equal to minus 3 is going to be my first equation. And then I'm going to have 3x plus 3y is equal to 3 is my second equation, but I can improve on my second equation by dividing 3 by 3. So I'm going to say that's just x plus y is equal to 1 for my equation 2. Right, we're running out of space here on the screen, so we're just going to go across here. We've got x minus y is equal to minus 3 is my equation 1. We've got x plus y is equal to 1 is my equation 2. I'm just going to do equation 1 plus equation 2. This will get rid of the y, so it'll give me 2x equals minus 2, which means x equals minus 1. Put that in a wee box, that looks right. Sub that into equation 1. So my equation 1 then is minus 1 minus y is equal to minus 3. So that's minus 1 plus 3 is equal to y, or y is equal to 2. And we'll write our answer down then as a coordinate. My answer is minus 1, 2. Okay, next we're going to look at transformations of a line. A linear transformation will map a straight line with vector equation r is equal to a plus lambda b onto the straight line with vector equation r is equal to a dash plus lambda b dash. Any point lying on the line a plus lambda b will be transformed to a point on the image line r is equal to a dash plus lambda b dash. Okay, a couple of things about this. If you have two parallel lines, they will And there we are. That's the two original parallel lines, and they are mapped. They go to something else. Their new images will still be parallel lines. So that's really about what we talked about earlier on about transformations, relationships being conserved. So if they're parallel, that means they're parallel. There's a relationship between them. And they're transformed. There's still a relationship between them. The other thing is any line which maps onto itself is said to be invariant. But it says here, and very importantly, it says any lines which maps onto itself is said to be invariant. Lines of the transformation. It is important to realize that there's a difference. So any line which is invariant under a certain transformation need not necessarily be made up of points which are invariant under the transformations. So an example is under a stretch parallel to the x-axis. The x-axis itself is an invariant line. So that means a point on the x-axis will move to another point on the x-axis, but the points themselves move. So say that, for example, the point 1, 0 would move to maybe 2, 0. So it has not stayed fixed itself, but it has moved within the x-axis. So very important. So you can have a line which is an invariant line, but it's not necessarily made up of invariant points, or you could have a line of points which are invariant. So it's very, very important to be clear on that. Okay, on to this example. It says find the equation of any lines that pass through the origin and map onto themselves onto the transformation, whose vector equation is 3, 2, 3, 4. Okay, so first thing to say is if a line passes through, I'll abbreviate this, passes through the origin, equation is y is equal to mx. Remember, the general equation of a line is y equals mx plus c, but c is 0 if you pass through the origin, so y equals mx. So I'm going to say let the general point be k, m, k. Now I could have used x and then mx, but I have just said k, mk. I've done it this way for years. I'm just going to keep doing it. So that means your new point x dash y dash is going to be equal to 3, 2, 3, 4 upon k, mk, and we're just going to multiply that thing out and see what we get. X dash y dash then is going to be equal to, it's now going to be a column vector, 3k plus 4mk, and then 3k, that top one should be 3k plus 2mk, 3k plus 2mk, and 3k plus 4mk. Okay, what were we talking about here? We're talking about invariant lines. So find the equation of any line that passes through the origin and maps onto themselves. So this is an invariant line. So that means invariant line, therefore y dash is equal to m x dash, and that's going to allow us to find a rule. So that implies that 3k plus 4mk is equal to m upon 3k plus 2k. So if we go up here and we work out with this, first thing you'll notice is we get rid of these k's. We'll do that now, just get rid of them, get them out of the way. So that's 3 plus 4m is equal to m upon 3 plus 2m. Multiply this all out and tidy up. You're going to have 2m squared plus 3m minus 4m plus 3. And we will go on with that. That's 2m squared minus m plus 3. Oh, it's a minus 3. That should be a minus 3, and that should be a minus 3 here as well, because that positive 3 is coming across. It's going to become minus 3. Okay, and then we can factorize that, right? I will not try and be smart about this. I will just go, my sum is equal to minus 1, my product is equal to minus 6. Minus 6 is equal to minus 3 times 2 is going to work for us. So 0 is equal to 2m squared minus 3m plus 2m minus 3. So take an m outside of bracket, 2m minus 3 upon, and then take a 1 outside of bracket, 2m minus 3. So the way I do this, I just write down the common bracket first, 2m minus 3, and then m plus 1, which means, lovely thing in mathematics, you've got 0 is equal to a times b, so that means either a is equal to 0 or b is equal to 0. So put a equal to 0, 2m minus 3 equals 0, implies then that m is equal to 3 over 2, and m plus 1 equals 0, implies m is equal to minus 1. So your answer, y is equal to 3 over 2 x, or your other line, your other option is y is equal to minus x, and that's it done. Okay, this next example says all points on the line y is equal to 2x minus 3 are transformed by the matrix 2, 1, 3, minus 1. Find the equation of the image line. Okay, we're going to start with a general point. So we're going to say general point on y is equal to 2x minus 3 is, and I'll use x this time instead of k, x, and then 2x minus 3. Okay, so when x is equal to x, y is equal to 2x minus 3. That's all that is. So all we're going to do is I'm going to say instead of x dash, I'm going to say big X and big Y instead of x dash and y dash, just to show you there's different ways to do this. So we have 2, 1, 3, and minus 1. And I've gone for x and 2x minus 3. And of course, all we're going to do here is multiply out and see what we get. So we have got 2x plus 2x minus 3. That's our top thing in our column vector. And then we've got 3x minus 2x plus 3. So tidy that mess up. You're going to have, top line, you're going to have 4x minus 3. And then you're going to have x plus 3. Okay, we will go over here. Right, so we've got x is equal to 4x minus 3, and big Y is equal to x plus 3. So we've got, basically we've got two equations, but we've got three things that we don't know. So we've got x is equal to 4x minus 3, and y is equal to x plus 3. What we're going to try and do here is we're going to try and eliminate, I'll just say eliminate your x. So it's a bit like a parametric equation, going from a parametric equation back to a Cartesian equation, a wee bit like that sort of method. So my second equation, I'm going to say my x is just equal to big Y minus 3. Therefore, big X is equal to 4 times y minus 3. So big X is equal to 4y minus 12 minus another 3. So big X is equal to 4y minus 15. Or you could rearrange that and write that any way you want. There's nothing wrong with that at all. So find the equation of the image line. So I'll just say my answer, x is equal to 4y minus 15. And that's it. Done. Okay, the next example is a very, very easy one. It says all points in the line r is equal to 1, 3 plus lambda minus 1, 4 are transformed by the matrix. Find the equation of the image line. Now you may remember we had at the start of the notes on this, we said that you have an original line r is equal to a plus lambda b. Then the image, if that's the original, then the image is going to be r is equal to a dash plus lambda b dash. So basically all we have to do is transform your a to your a dash, transform your b to your b dash, and then put them back into the vector equation. So all we're going to do here is do 2, 1 minus 1, 1 to your a, which is 1, 1, 3. And if you do that out, first row, first column, so that's going to be 2 times 1 plus 1 times 3, that's going to be 5. And then second row, first column, it's going to be minus 1 times 1 is minus 1 plus the 3 is going to be 2. And then same idea, we're going to do our 2, 1 minus 1, 1 to whatever it was, minus 1, 4. So first row, first column, that's going to be 2 times minus 1 plus 4, so that's minus 2 plus 4 is going to be 2. And minus 1 times minus 1 is 1, plus another 4 is going to be 5. Okay, so your answer, your image line is r is equal to, so this was my first bit here, so it was 5, 2 plus lambda, and this was my second bit, it was 2, 5, done. Okay, this next example, we have to describe the transformation given by the matrix 2, minus 1, 1, and 0. So it's a bit like something we did the other day, where we were looking at transforming our matrices. So we have to see what happens. So we said back then, we said we would look and investigate what happens when you transform what we called the unit square. So the unit square, the coordinates of the unit square are as follows. And we're going to transform that, and I'm going to rush through this here. This, by now, we should all be fairly good at multiplying out our matrices. Right, now the hard part here is drawing this, especially on this tablet. There's my unit square, there's my origin, there's my point A, there's my point B, and there's my point C. And if you notice here, my origin stays fixed, my point B stays fixed, stays at 1, 1, and my point C then moves to minus 1, 0. So this is my C dash here, and my point A starts off at 1, 0, and it moves across to 2, 1. So my A moves up to here. Now this is going to be the hard part about drawing this, but what we should notice is A and B stay fixed. So this, whatever line that these, O and B stay fixed. So whatever line O and B are on is going to be an invariant line, and you should realize that this line that they are going to be on is y is equal to x. The 45-degree diagonal line, y equals x. So we have to link this all up. So you can imagine you've got a line going here, and C goes back to B. B goes out, or B dash as well. B goes out to A dash, and then that goes back to 0. So it forms a very ugly way I've done it, but it forms a parallelogram. So C dash O obviously is parallel to B A dash, or B dash A dash, and that's what it is. So what you've got is an invariant line. Oh, forgot to say what it was. It was a shear, but with an invariant line, y equals x, st, such that, and then just pick one point that you know that moves. So the point that I'm going to pick that moves is my A, which is 1, 0, and it goes to 2, 1. And that is the first bit of it done. Okay, on to part 2. The curve 5x squared plus y squared minus 4xy minus 12x plus 6y equals 0 is transformed by the matrix. Show that the equation of the image curve is given by x squared plus y squared minus 6x. So the first thing we've got to do here is get rid of that thing. Show that the equation of the image curve is given by x squared plus y squared minus 6x equals 0. Okay, so part 2, we're going to just say let xy be the general point on whatever it was originally, 5x squared plus y squared minus 4xy minus 12x plus 6y equals 0. And what we're going to do is just transform it by our matrix. I'll write that matrix down before we lose it here. So we're just going to say big X, big Y equals 2 minus 1, 1, 0 upon small x, small y. And we're going to just multiply it out and see what we get. Okay, we'll get rid of that and see what we get. So when we do that, you're going to get big X, big Y equals, and that's going to be 2x minus y, and that's just going to be x for the next one. So we've got big X big X equals 2x minus y, big X equals 2x minus y, big Y equals x. So we'll just write those out again. Big X equals 2x minus y, big Y equals x, and we're just going to sub into the image equation and see what happens. So what was the image equation? There it is, x squared plus y squared minus 6x equals 0. So sub into x squared plus y squared minus 6x equals 0. So if you sub that in, you have 2x minus y all squared plus my y, which is small x, minus 6x, which was 2x minus y. Oh, and what I nearly made a mistake, which we're definitely not meant to do. You do not put that into equal to 0. Strictly, this should not be equal to 0. So we're just going to sub this into this thing and see what it is. So we've x squared plus y squared minus 6x. We've subbed in our values. So you've instead of x, you've big X, you write 2x minus y. Instead of big Y, you write x. So that's what you've got. Okay, if you go on, and the next thing we're going to do is just multiply this out and tidy up and see what you get. So if we go on here at this stage, multiply this out. Skipped a wee bit of working out here, but it should be fine. 4x squared minus 4xy plus y squared plus x squared minus 12x plus 6y equals, tidy this all up, what have we got? 4x squared. I've got a y squared term. I've got I have another x squared term. So that really is going to be 5x squared. 5x squared plus y squared, and then I've got minus 4xy minus 12x plus 6y. And let's just go back up to the top and remind us we had 5x squared plus y squared minus 4xy minus 12x plus 6y. So now we can say, and this is the first time we should put in the 0, which equals 0, and then you just write from above. And read the question again. In what way did they ask it? So just say, if this equals 0, equals so therefore x squared plus y squared minus 6x equals 0 also. So the image curve is x squared plus y squared minus 6x equals 0. Okay, and that's that one done. Okay, next example is similar to the previous one. It says a set of points which form the curve whose equation is x squared plus y squared minus 8x plus 8y plus 2xy equals 0 is mapped by the matrix minus 1, 1, 1, 1. Show that the curve formed by the image points has equation y squared plus 8x equals 0. So same idea. Again, we're just going to say let let xy be the general point on x squared plus y squared minus 8x plus 8y plus 2x y equals 0. So we're just going to say big X, big Y is equal to minus 1, 1, 1, 1 times small x, small y. And we're just going to multiply that out and see what we get. So that's now a column vector, minus x plus y and x plus y. And if we do that out, then we're just going to investigate. So we're just going to say, we'll write that out again as the equation, minus x plus y, and y is equal to x plus y. We'll go on down a wee bit and just say here, sub into y squared plus 8x. So don't write down equals 0 like I did in the last one at the start. Please don't put that in at this stage. It's as if it's a big reveal that we're showing, oh, this is equal to 0, happy days, and then we know we're right. So don't put it in at the minute. Don't put it equal to 0 at the minute. Just sub in your values. So our values were x plus y squared, and then 8 times my x, which is minus x plus y. So if we work on down with that, you're going to get x squared plus 2xy plus y squared minus 8x plus 8y, and we'll move up here because we've run out of space. So that is equal to x squared plus y squared minus 8x plus 8y, and then plus 2xy. We'll say which equals 0, and we'll just say from above, therefore big Y squared plus 8x equals 0, i.e. equation of image is y squared plus 8x equals 0. Done. Okay, right folks, apologies for the stop-start sort of video there. I kept getting interruptions from a 3-year-old, but there we have our questions we can now do. It's exercise 6C, questions 1, 3, 4, 5, 7, 8, 10, 13, 14 and 17. And any problems, give me a shout.